Welcome to reaction mechanisms. So far, we've considered reactions as occurring in a single step when we're talking about reaction rates. We saw this in 11.3 with the reaction A plus B yields product AB. The single step here is A combining with B, and because this happens in one step, we call this an elementary reaction. We also saw that we could represent the rate of this reaction as rate equals a specific rate constant times the concentration of A times the concentration of B. The concentration of the reactants are multiplied with each other. And when we looked at where this expression came from, it came from the fact that A has to collide with B. And the chances of A colliding with B, that probability is proportional to A times B. So this expression comes from a collision between A and B. And this has to be a simultaneous collision between a particle of A and a particle of B. If we instead consider the reaction of A plus B plus C yielding some products, by the same reasoning, this reaction would have to have a simultaneous three-way collision between A, B, and C. And not just a simultaneous collision, but a successful collision. So not only do all three have to hit each other at the same time, but they have to hit each other in the proper direction. And while that's in the realm of possibility, it's probably not very likely to occur. So it's more likely that the overall reaction of A plus B plus C yielding products occurs in a sequence of steps. For example, the first step, we'll call it S1 for step 1, could be A plus B colliding together and forming a temporary product AB. Then the collision between AB and C yield the actual products. In this case, AB is an intermediate. It's not the final product, and it doesn't show up outside the sort of in-between step. So we have step 1 where A and B combine to form AB, and then we have step 2 where AB combines with C to form the products. Together, S1 and S2 are called the reaction mechanism. Now, step 1 and step 2 each have their own delta H's, their own changes in enthalpy, and if I add up these reactions, just like with Hess's law, first of all, I'll get back the original overall reaction, and second of all, if I add up the delta H's, I'll get the overall delta H of this reaction. But aside from that, they each have their own rates. So the rate of step 1 is going to be equal to a specific rate constant times A times B. The rate for the second step, however, is going to be based on the reactants for that second step. So it's going to be another specific rate constant times the concentration of AB and the concentration of C. Now this is where it's a little bit different. For heat of reaction, we add stuff together to get the overall reaction. We can even add up the steps to get the overall reactants and products. But we don't add the rates together. That's not how the rates work. I'm just going to make this up now, but let's say that the rate of step 1 is slow and the rate of step 2 is fast. That means the overall rate, or the rate of the overall reaction, A plus B plus C yields products, is equal to K1 times A times B. The reaction can only go as fast as its slowest step, and that gives this step a special name. This is the rate limiting step. And the slowest step of any overall reaction or of any reaction mechanism, that individual step is called the rate limiting step because the reaction can't go faster than its slowest step. I could have a reaction mechanism with 20 steps, and say 19 of those steps took half a second to accomplish. But say step number 7 took 3 years. That means the overall rate of reaction also has to be 3 years. That's just the nature of the rate limiting step. That wraps up our lesson on reaction mechanisms and the rate limiting step. Write down any questions you have in your notes and bring them with you to class.